So, today we will discuss metal olefin complexes. For the first time in this series, we are going to look at compounds where the metal is bonded to two carbon atoms simultaneously. In organometallic terms, one often indicates the formation of an olefin complex by writing them as M coordinated to two carbons by drawing a line in between the two carbons. And in the nomenclature, one indicates this as an eta 2 complex, meaning both carbon atoms are bonded at not necessarily equidistant, but almost in a similar fashion, so that both carbons are interacting with the metal simultaneously. So, in these systems, the olefin, which is usually, if you consider the four atoms which are bonded to the olefin, I will label them as A, B, C and D. If A, B, C and D and the two carbons are in a plane, then the metal is in a position below that plane. So, the metal itself is in a plane below the plane which is containing the four atoms A, B, C, D and the two carbons which are interacting with the metal. So, let us take a look at some of these complexes. It is interesting that there is a very similar bonding pattern between olefins and metals and carbon monoxide and metals. The give and take of electrons that we discussed with metal carbonyl complexes exists with metal olefin complexes also. So, the type of syntheses that we encounter in metal olefin complexes are very similar to what we encounter in metal carbonyls. So, let us take a look at a few of the synthetic methods, then we will examine a few structures and the bonding pattern in these molecules today. So, synthesis of olefin complexes in general involves a simple ligand substitution. So, a carbon monoxide ligand can be substituted by an olefin. One can also reduce a metal salt in the presence of an olefin, and this is exactly what we did for carbon monoxide. We used to reduce the metal salt in the presence of carbon monoxide, sometimes at high pressure, and that led to the formation of a metal carbonyl complex. If you want to make a metal olefin complex, we can do the same trick, namely take the metal in a higher oxidation state, reduce it with a suitable reducing agent, which will not reduce the olefin, and under those circumstances, we can prepare a metal olefin complex. There is also a specialized method called the metal atom synthesis, and in the metal atom synthesis, one generates a vapor of the metal, which will co-condense with the olefin or any ligand of interest. If we can do that, then a metal olefin complex can be generated without interference from any other ligand. Finally, one can in some instances take an unsaturated complex and add an olefin, and that will lead to a metal olefin complex. So, let us take a look at some very simple methods of generating metal olefin complexes. So, the group 10 elements, which are usually the ones having a D10, it is actually group 11, which has a D10 complement of electrons, and so they are oxidized to the +1 oxidation state. So, silver 1, gold 1 and copper 1 are suitable examples. So, you can very easily make these olefin complexes, especially the copper and the silver metal complexes, by simply taking the metal salt and reacting them with an olefin. All you have to do is to keep a non-coordinating anion, and if you take a nitrate for example, it is quite efficient as a non-coordinating anion, and you can treat it with an olefin, a suitable olefin. A weak complex is formed. Now, you might be wondering, why is it a weak complex? You remember that the type of interaction that is involved in this give and take of electrons between the metal and the olefin, you need the metal to be present in a state which is ready to give electrons to the antibonding orbitals of the olefin in this instance. The carbon monoxide case was also similar. To form a carbon monoxide silver plus complex or a copper 1 complex, it was quite difficult because the back bonding is poor, and so necessarily you form weak complexes. But nevertheless, these complexes are extremely useful because the weak interaction is convenient for establishing an equilibrium, and any application that requires only a weak interaction will benefit from such a situation. So, the common application of silver complexes is that one can coat chromatographic columns with silver ions, and then this weak interaction is sufficient to distinguish between various olefin complexes. So, in other words, the stability constant of two different olefins, if they are different, if you can have the cis and the trans isomers of 2-butene, they can be very easily separated utilizing this trick, because the stability of the trans butene is less than the cis butene complex. And this is something which we will consider later in detail, but suffice it to say that this stability difference is able to differentiate between these two olefin complexes in terms of the stability constant, and hence the rate at which a silver coated column will discriminate between the trans and the cis butene. So, a similar situation occurs with the copper complex. If you take a copper 2 plus ion, you can reduce it with copper metal in the presence of a solvent like acetonitrile CH3CN. The key to this reaction is the fact that you have a non-coordinating anion or a weakly coordinating anion, the perchlorate anion, and also the fact that you have a stabilizing solvent. Copper 1 is stabilized in the presence of acetonitrile, because acetonitrile is a pi accepting ligand, and so it stabilizes the lower oxidation state of copper. In this case, it is copper 1. So, it is possible to make copper perchlorate, which is in the +1 oxidation state, which I have put within quotes, because this itself is an unstable system. This is unstable, and it is only stable if it is present in the if acetonitrile is also present in the medium. So, one can use other non-coordinating anions very conveniently. The other ligand which is very commonly used is the triflate counterion. So, copper 2 triflate is taken, and the reduction is carried out with copper metal, which is the most convenient because no other interfering metal is present in the medium. So, you take copper 2 plus, reduce it with copper metal, and in the presence of triflate or perchlorate or nitrate, and then you can reduce it to the copper 1 state, and if an olefin is present, you can form the metal olefin complex fairly readily. But as I mentioned, the copper and the silver salts are reasonably stable, but they cannot be used extensively because they tend to decompose. The reduction can be carried out electrochemically. This is sometimes convenient if you use 2 copper electrodes and do and try to pass current in the presence of acetonitrile and an olefin. The olefin complex will be formed when the copper 2 plus in solution, a copper sulphate solution can be taken, and the reduction can be electrolysis can be carried out with copper electrodes. It is convenient to do so. Then the anode and the cathode get coated with the copper 1 compound, especially if the solvent is sufficiently stabilizing, one can get very good yields of the copper 1 complex. Now, it is not always necessary to reduce the metal from the higher oxidation state to the lower oxidation state using a metal. Here is an example where ethanol functions as a reducing agent. Ethanol gets oxidized to acetaldehyde. So, ethanol gets oxidized to CH3, CHO. In other words, 2 hydrogens have been removed from ethanol, and those are the reducing elements, they reduce the rhodium chloride to rhodium 1, rhodium 3 chloride. Here it is present in rhodium 3 and here it is present in the rhodium 1 oxidation state. And you can see that because you have 2 rhodiums with 2 chlorines. Now, in the presence of acetylene, if in the presence of ethylene, you will form a rhodium 1 complex, and in this case it is 2 rhodium atoms coordinating to 4 ethylene moieties, and this complex is quite stable, and because ethylene is quite volatile, this can also be used as a precursor for making other olefin complexes. So, this is yet another way of reducing the metal salt and generating the metal olefin complex. So, let us take a look now at some other a few more complicated methods. In this instance, you have a bis cyclopentadienyl cobalt complex, and as you know, ferrocene is the only bis cyclopentadienyl complex that has got an 18 electron structure in the +2 oxidation state. So, cobalt obviously has got more number of electrons than necessary to form an 18 electron system. Since cobalt has got 9 electrons, it has 1 electron more, and if you pump in 1 more electron using say potassium, potassium is the reducing agent which will become K plus, and it will add 1 electron to the medium, and this 1 electron will add on to the cobalt, and so cobalt, if it becomes cobalt minus 1, this turns out to be a 20 electron complex and it is quite unstable. What it does is that it liberates cyclopentadienyl anion with potassium as the counter ion, and during this process cobalt from the +2 oxidation state, it is present in the +2 oxidation state, it has got reduced to cobalt 1, and the cobalt 1 is now coordinated to 2 ethylene molecules which are in the reaction medium. So, this complex can be drawn as follows. You can have 2 ethylene moieties which are bonded in a symmetrical fashion to ethylene, to the cobalt 1 species which is present in the center. Although we have not studied cyclopentadienyl complexes up to now, we can understand that because we have 5 carbons coordinated to the cobalt 1, they will in the neutral method give 5 electrons. So, the neutral method, we will have 5 electrons from cobalt and 9 electrons from cobalt, 5 electrons from the Cp, and 2 electrons each from these olefins, and so we have 4 electrons from ethylene. So, we have a total of 18 electron. So, 18 valence electron complex is formed very conveniently, and this turns out to be a stable system. So, this moiety is in fact known for cobalt, rhodium, and the rhodium complex is extremely interesting, and if time permits, we will look at the structure of this complex and the type of interactions that can be there in the system. Now, the most famous olefin complex that is present in the literature, that is available in the literature, is what is called the Zeiss complex. The Zeiss complex has in fact a very strange complex that was formed, and it was accidentally discovered by Zeiss when he boiled potassium tetrachloroplatinate with ethanol, and finally, it was found out that it was an ethylene complex that was present in the product. So, there was one ethylene moiety which is coordinated to the platinum, and there are 3 chlorines. Because platinum is present in the +2 oxidation state, it has got a negative charge, and this negative charge is now balanced by a potassium ion. So, we started with a platinum 2 complex. We have not carried out a reduction here, but what we have done is we have generated ethylene, and we have used ethylene in the reaction medium and coordinated the ethylene to the platinum, which kicks out one chloride ion and forms an ethylene complex. So, this is an example of a simple substitution. There is no reduction involved. So, this is an example of a simple substitution reaction. A chloride ion is replaced by an olefin, and because the olefin is reasonably strongly bound to platinum 2, in spite of the fact that the oxidation state is +2, platinum, because it is a lower group element, it has got sufficiently large orbitals. It interacts very conveniently or very readily with ethylene, and it forms a nice olefin complex. Now, a few words about this complex is pertinent here. One of them is the fact that the complex is found in the presence of water. This whole reaction was done with dilute hydrochloric acid, and notice that the structure of the molecule is also containing the lattice. The crystal structure of the molecule is also containing a molecule of water. So, this is very strange, because one often thinks that organometallic compounds cannot be synthesized in the presence of water, and the very first olefin complex that was synthesized, and that was way before the discovery of ferrocene, it had a molecule of water in the lattice to begin with. And it also was made by boiling it in dilute hydrochloric acid with ethylene. So, simple substitution reactions are possible with several elements, especially with elements which have either a D8 configuration and they have only 4 ligands around the coordination sphere. It is very easy to add a ligand or to substitute a ligand. So, here is an example. Here is an example with rhenium. You notice that rhenium is again interacting with ethylene molecule, and in this instance what has happened is AlCl3 in the reaction medium, AlCl3 has grabbed this chloride ion. So, this chloride ion has been grabbed by the aluminum. In the process, an ReCO5 plus moiety has been formed. An ReCO5 moiety will be coordinatively unsaturated, and it grabs the ethylene and forms an ethylene complex, and the counter ion is now AlCl4 minus. Another example is the generation of a vacant coordination site in the complex by using a silver salt. By using the principle that silver 1 ion is halophilic, it will tend to react very readily with any halide ion in the coordination sphere of a metal. Here we have taken an iron complex which has got an iodide, and the iodide is removed by the silver. So, the iodide and silver react together and form silver iodide, and this silver iodide is now removed, and that leaves a vacant coordination sphere on iron, which leads to the formation of an olefin complex, which we have pictured here. So, in all these examples, either there is an assisted removal of a ligand from the coordination sphere of a metal complex, and that vacant coordination sphere is occupied by an olefin. Notice in all these examples we have used simple ethylene. In fact, ethylene forms a very strong complex with metals, and substitution in fact destabilizes the system, except under some special circumstances which we will look at in a few minutes. In coordination chemistry, it is possible to have more stable complexes formed when you have 2 places of attachment for the ligand. So, in other words, if I have a metal complex where 2 NH2 groups are present on the ligand, then the coordination of both NH2 groups to the metal turns out to be a more stable situation than when you have a single point of attachment. So, CH3NH2 coordinated to a metal versus CH2 versus ethylene diamine coordinating to a metal. These two systems are differentiated by the so called entropic effect, the chelate effect, which leads to more stable complexes. A similar situation can happen in the case of olefins, and here we have pictured cyclooctadiene, which is written in a convoluted form purely because it has to bend in that fashion in order to bind to the metal, so that both olefin faces can be facing the palladium atom. So, here you have a weakly coordinating benzonitrile PHCN that leaves the coordination sphere of palladium, and the cyclooctadiene is a chelating ligand. It is a olefin complex, but it is a chelating ligand, and it can now conveniently form a metal olefin complex. Now, it is also possible for us to replace a carbon monoxide. As we had mentioned when we discussed substitution reactions, carbon monoxide in metal complexes can be readily displaced, especially in the transposition, if one can use a ligand which will not compete with carbon monoxide for pi accepting property. Although I mentioned in the beginning of this lecture that ethylene can have pi accepting property, it is not as good a pi acceptor as carbon monoxide. Carbon monoxide, as I mentioned to you earlier, is a ligand par excellence. It is the only ligand which has got extremely good pi accepting property, and it is very convenient to use it in a variety of situations. But when you want to do a substitution reaction with an olefin, the trans carbon monoxide gives way, so that one carbon monoxide will have better pi accepting property from the metal, and a weakly coordinating ligand can be present in the coordination sphere. And here we have iron in the 0 oxidation state. It is a 18 electron complex where carbon monoxide has been displaced, so that the other two carbon monoxides which are present in the same plane will have better pi bonding characteristics from the iron. So, you are replacing one pi accepting ligand by a weaker pi accepting ligand. This again is a general principle, and we have managed to do this in this instance with this diethyl malate, which is a good ligand for replacing the carbon monoxide. Now, I have mentioned that ethylene is a good ligand for metal in 0 oxidation state, but very often it is not possible to prepare homoleptic complexes. By homoleptic complexes, I mean only those complexes, only those ligands which are present around the metal are of the same type. They are in this case an olefin. So, it is possible in a few instances to prepare homoleptic complexes with olefins, and one example is when you can reduce nickel dichloride with trialkyl aluminum, and when you do that in the presence of ethylene, you can prepare a tris ethylene complex of nickel. Unfortunately, this complex is not very stable. This complex is not extremely stable and is stable only up to a temperature of 0 degrees centigrade. So, this is useful, but nevertheless, it is not a stable system. A slightly more stable system is a bis cyclooctadiene complex of nickel. Here, because of the chelate effect, the stability is increased. Nickel is again in oxidation state of 0, and so you have a D10 system. So, you have a D10 system, and this D10 system now has got 4 olefins coordinated to it in such a fashion that it is almost like a tetrahedral complex of ethylene. Here you have 2 cyclooctadienes and it is quite much more stable than the ethylene complex, which is a 16 electron complex. So, the nickel complex with 3 ethylenes is a 16 electron system, with 2 cyclooctadienes it is an 18 electron system, and this is 18 electron system is much more stable, and this can be isolated and characterized very easily. Now, I want to talk about displacement of one olefin by another olefin. Now, this is not the method of choice for making olefin complexes, but in a few instances ethylenes can be replaced by another ethylene or an olefin. Now, this has to, if it has to be thermodynamically viable, the complex that is formed must be much more stable. The complex that is formed must be much more stable than the complex that was present initially. And when you replace ethylene with a cyanoethylene or acrylonitrile, then the stability increases. This must be an electronic effect, because any time you have a substitution on ethylene, the stability usually goes down. But in this instance, it has increased, and it can be seen immediately that if you put an electron withdrawing substituent on the ethylene, this leads to greater stabilization, because the pi star orbital on acrylonitrile, the pi star orbital is at a lower energy level, and from the nickel the electron density can flow into the pi star orbital more readily, and so the back bonding is greater in this instance. So, the greater degree of back bonding, in these complexes leads to greater stability. Now, let us move on. There is one unusual method of synthesizing metal olefin complex, and this is by removing a hydride ion. If you take the trityl cation, the trityl cation is the one which is a cation which is stabilized by the presence of 3 phenyl groups, and this can abstract a hydrogen atom. And if it abstracts a hydrogen atom from an alkyl complex, which we have already learnt about, if this hydride is abstracted by the trityl cation, then one ends up with ethylene complex. In this particular case, it is a propene complex which is formed, and this propene complex is quite easy to or conveniently isolated using this method. So, alkyl complexes can be converted to olefin complexes in a few instances by the use of this trityl cation. Now, we have discussed a few methods of making metal olefin complexes, and we have discussed during this process the reasons for their stability, but let us just systematize them and collect our thoughts together. First of all, we said that carbon monoxide can be replaced by olefins in the transposition, and this is possible because carbon monoxide is a stronger pi accepting ligand, and it will displace the carbon monoxide in the transposition and replace it with an olefin, and this will lead to greater stability because the olefin itself is a poorer pi acceptor. So, the metal is able to donate more electron density to the carbon monoxide, and the MCO bond becomes stronger, and this leads to greater stability. So, a second example that I told you about is the replacement of an ethylene with acrylonitrile, and acrylonitrile, because of its greater pi accepting property, it also can replace a simple ethylene. Here again, we are talking about better pi accepting character of the olefin, but in this instance the pi accepting property of the olefin that is coming in is much better, and so the nickel 0 complex that we had on the reaction side, on the reactant side, this complex turns out to be less stable than the acrylonitrile complex, purely because on the right side we have better pi accepting property. So, the pi accepting property goes up in this instance, and so you have greater stability. So, apart from these electronic effects, we also have very significant steric effects in the case of metal olefin complexes. And usually it is seen that the trans complex is less stable than the cis complex if there are two substituents, and the monosubstituted complex is always more stable than the disubstituted complex. And of course, the ethylene was the best ligand. When you have no electronic effects to talk about, then the ethylene complex is in fact the best system to study. So, the steric effects play an important role, and we will see in a few minutes why this is the case. Let us take a look at the complexes in greater detail, the structural aspects. You have eta 2 bonding, which means both carbons are equally bound, and all the hydrogens, if they are ethylene, if it is an ethylene, there are 4 hydrogens, all 4 hydrogens are equidistant from the metal. The back bonding that we have referred to, which means the metal gives electron density into the pi star orbitals, lengthens the carbon-carbon bond. So, you have a carbon-carbon bond which can lie anywhere between a C-C double bond to a C single bond C. And if there is such a back bonding interaction, we will see in a minute that there is a barrier to rotation of the olefin with respect to the metal carbon metal olefin axis. So, if this is the olefin that we are talking about, then in this axis you can rotate the olefin or the metal complex with respect to the olefin, but this rotation has a barrier, and this is because of pi interactions between the metal and the olefin. All these factors have to be explained, and we will be able to explain each one of these factors using some of our structural features. Here I have indicated that the carbon-carbon bond length in ethylene is 134 picometers, or if you prefer the angstrom unit, it is 1.34 angstroms. And if one forms the complex, then the carbon-carbon bond length increases. Similarly, the frequency of the carbon-carbon double bond stretch, the stretching frequency in ethylene itself is 1623 centimeter minus 1. And when it is coordinated to platinum, as in Zeiss salt, it is reduced remarkably. It goes down by about 100 centimeter minus 1, and this is exactly the ballpark figure we obtained for carbon monoxide complexes also. When you interact a carbon monoxide with the metal, then if the metal is in the 0 oxidation state, the metal is capable of putting electron density into the pi star orbital, and similarly here in this instance it is putting electron density into the pi star orbital of the olefin, and we will picture that in a few minutes. So, here is the initial interaction, and we have already discussed the people who have discovered this type of bonding, Dewar, Chatt and Duncanson. Dewar, Chatt and Duncanson are the 3 people who developed this mode of bonding. So, the primary interaction in this mode of bonding is the donation of electron density from the ligand. So, this is the ligand that we are talking about, and here is the metal, and usually the ligand donates electron density to the metal, and we have pictured that here. It is giving electron density to the metal from the filled pi orbitals of the olefin. So, the filled pi orbitals are present, and they do not have a node between the 2 carbons. So, here are the 2 carbons, and the 2 carbons have a pi cloud on either side of the carbon, and one side is capable of donating electron density very significantly into an empty orbital on the metal. So, this is the sigma bond. People have estimated that this sigma interaction involves transfer of about 0.24 electrons 0.24 electrons from the ligand to the metal. So, although we call it a 2 electron donation, the 2 electrons are present in the olefin, but approximately 0.24 electrons are transferred, or at least 24% of the electrons, or about 12% of the pi electron density is transferred completely to the metal. So, this is the sigma interaction. We call it sigma interaction because one can rotate the olefin about this axis, and you will not lose any overlap as you rotate the olefin. So, let us take a look now at the pi electron pi interaction. Again, this is part of the Dewar-Chat-Duncanson model of bonding, and what we have is a pi star orbital of the ethylene now interacting with a filled orbital on the metal. So, here is the metal and here is the olefin. The 2 carbons are present here, and the pi star interaction involves an antiphase overlap of the 2 p orbitals on the carbon, the ones that are not hybridized to interact with the hydrogens. And so, this pi star orbital now accepts electron density from the metal into the empty orbitals on the olefin. So, the situation is very similar to what we encountered in carbon monoxide. Electron density from the metal is going into an antibonding orbital, and the symmetry of this interaction is a pi interaction, because you will notice that if I rotate the metal or the olefin with respect to one another around this axis of interaction, then the bonding is immediately disrupted and there is a breakage of this bond. So, this must involve pi symmetry. So, these are pi interactions, and people have estimated that in this pi interaction about 0.22 electrons are transferred from the metal to the olefin. So, almost equal amounts of electron density are transferred from the ligand to the metal and from the metal to the ligand. Now, if one can believe these calculations, then one can say that there is a slight excess of electron density transferred from the ligand to the metal, and so the sigma bonding is a little bit more important than the pi interaction. But you can see that it has to be a synergistic interaction. If you donate more electron density to the metal, then the metal in turn can donate more electron density to the pi star orbital. So, this Dewar-Chat-Duncanson model promotes or suggests that there is a synergistic interaction between the metal and the olefin. So, here I have summarized both, pictured both in the same slide, and you can see how the 2 interactions complement one another, and it is a completely synergistic interaction. One of course has sigma symmetry and the other has got pi symmetry. So, rotation does not break this bond, whereas this bond is completely broken. The pi bond is broken when you rotate it. So, that is why you have a small barrier for the rotation of an olefin. This barrier can be pictured here in the Zeiss complex. I have illustrated it for you, saying that if the 3 chlorines around the platinum are in the xy plane, if you think that this is the xy plane, then the ethylene is parallel to the z axis. The ethylene carbon-carbon axis is parallel to the z axis. So, that is how we want to talk about this interaction. Then the Dxz orbital, if this is the x axis, then the Dxz orbital is the one which would be suitable for interacting with a pi star orbital on the olefin. So, the Dxz orbital is pictured here, and the Dx squared minus y squared orbital will be the orbital which primarily accepts electron density from the pi. From pi of the olefin, electron density flows into this, and from the Dxz it flows into the pi star orbital of the ethylene. So, I hope you will be able to appreciate this dual interaction that stabilizes metal olefin complexes very significantly. And as I mentioned earlier, you do have a barrier to rotation this is the original geometry that we talked about. If you rotate it, you will end up with the 4 carbons, the 4 hydrogens on the carbon, the same plane as the PTCl3 moiety. They will all be in this particular plane, and when you do that, then you end up with some steric interactions which destabilize this situation. But you will notice that the Dxy orbital on the platinum and the pi star of the olefin can interact just as much as the Dxz was able to interact with the pi star. So, here Dx in this orientation, Dxy can pump in electron density into the pi star of the olefin. So, both ways you can have pi interactions. The sigma is not disrupted at all, but the pi star can also be there in this orientation, but because of steric influence you do not have a very stable situation. So, the steric interaction is pictured here. In general, it's more important when you have a bulky group in this position, then it interacts with the chlorine significantly, but even with an ethylene, the molecule prefers this orientation much better, and so that is the more stable crystallographically characterized system. So, let us move on. Let us take a look at a few of the characteristics that are significant. One is the fact that you have slight rehybridization of the carbon. The carbon in the ethylene, in simple ethylene, it is hybridized in a sp2 fashion. So, the carbon has got an sp2 hybridization. Now, when it is bonded, it seems to have a slight rehybridization at the carbon center, and that leads to a bending of the hydrogens away from the metal. So, if the metal is bonded in this position, then the hydrogens are moved away from the metal, and this moving away leads to a slight rehybridization of the carbon, and various explanations have been given for this particular explanations. We just talked about the mild steric interaction that can be present. There is also an electronic effect that makes the carbons bend away in such a fashion that there can be better overlap between the metal and the carbon orbitals. So, initially carbon-carbon bond distance is around 136 or 134 picometers. Here it is 1.34 angstroms, and it can, in the complex, they go all the way from 146 picometers or 1.46 angstroms to even 1.54 angstroms, and this is the distance that you have for a carbon-carbon single bond. And surprisingly, the back bonding can be more and more significant in some instances, especially if you have electron withdrawing groups, and then the bond distance can increase all the way to 1.54 angstroms. Now, if you have a cumulene where you have 2 double bonds consecutively, then the central carbon, we are talking about systems like this, then the central carbon is sp hybridized. So, these are allenes, and these allenes get significantly bent when you are binding them or interacting them with a metal atom. Here I have pictured a platinum atom which is interacting with an allene moiety, and the angle in the free allene is 180 degrees, and there is no difficulty in understanding that, because the central carbon is hybridized with an sp hybridization. But the moment you have interacted with an olefin, then the strain of the central carbon is released, and it moves towards the 120 degree angle that you would end up with in a sp2 hybridization, and it becomes close to 142 degrees here. The carbon-carbon bond distance is around 148 picometers, and it is close to the carbon-carbon double bond distance. Now, let us take a look at the frequencies of metal olefin complexes, because this is also interesting. As I mentioned, the free olefin is 1.34 angstroms or 134 picometers. When it is bonded to a metal, then the bond distance increases and the frequency decreases. So, you can see about 100 or less than 100 centimeter minus 1 decrease in the metal olefin. You have a 100 centimeter minus 1 decrease in the carbon-carbon stretching frequency. So, this frequency is talking about the carbon-carbon stretching frequency here, nu Cc, and this is the C double bond C distance that we are talking about here. You will notice that when you have a 4D or a 5D element, then the bond distance is different. There can be greater or more pi interaction between the metal and the olefin. And if you have a metal in a 0 oxidation state, then the pi interaction, the bonding between the two carbons is decreased even further. So, if you have iron in 0 oxidation state, this is a complex with iron in 0 oxidation state, the bond distance is 1.46 angstroms, it is long, whereas in the case of rhodium 1, this is a +1 oxidation state, and so back bonding is less, and so the olefin has got a shorter bond distance. So, this is less pi interaction in this case. So, the discussions that we had with carbon monoxide with respect to greater pi back bonding and greater pi bonding resulting in frequencies that are smaller or greater reduction in stretching frequencies hold good in this instance also. If there is less back bonding, then the bond is stronger and the frequencies are higher. So, there is inverse correlation between the two of them. So, how do we know how much the metal is interested in pumping electron density back into the olefin? One way to measure this is to look at the ionization potential for the metals, and here I have listed a few of the ionization potentials, and you will notice that as you go down the group, you tend to have a remarkable change in the ionization potentials. Nickel is easiest to ionize, it is easy to remove the electrons from nickel 0, that is also a D10 system. Platinum 0 is also a D10 system, but it requires almost 2 times the amount of energy to remove the electron density from platinum. But the platinum complexes with olefins are extremely good purely because in spite of this higher energy of ionization, higher energy required for ionization, it is possible to have good overlap between the platinum and the olefins. In the case of nickel, one realizes that it is easy because of the fact that you have a 3D element, and this also results in very good bonding between the two systems. Palladium 0 should not, by what we are seeing here in terms of ionization potential, nickel and platinum should form better complexes than palladium, and that is in general true. So, let us take a look at the rhodium and the iridium complexes. Once again, the rhodium complex is easier to ionize and the iridium complex has got a higher ionization potential, and so rhodium forms very good complexes, very stable complexes. We have seen a few of them in the last few transparencies. Similarly, copper and silver, because they are positively charged, they are already oxidized, they have very high ionization potentials, they form weak complexes. So, these are systems where they have weak complexes and you have no complexes with zinc 2 plus. So, let us proceed further. In the time that we have, let us take a look at the donor acceptor properties. Can we correlate the donor acceptor properties with the pi accepting property on the stability of the complex? In general, the stability of the complex, if it is plotted on the y axis, if it keeps increasing, if you have very good electron accepting groups on the olefin, then they form stable complexes. So, you have trans dicyano compounds. So, you have CN and CN, then it forms a much more stable complex with the metal, because you can have better pi accepting property. Whereas, if you have no substituent, then you have poorer pi accepting property, and that is pictured around here. And then you have systems which have got substituents which prevent the close approach of the olefin to the metal. So, if you have cis, it is more stable than trans. We have already explained this, because trans cannot twist in such a way that it can approach the metal in a closer fashion, whereas cis, by bending the substituents on the carbon-carbon double bond in such a way, it can move it away from the metal, and so it can have better interactions. And so, this is the monosubstituted systems, and then this is your ethylene itself, simple ethylene, and these are with weaker electron accepting groups. The systems which are pictured here have weaker electron accepting groups. So, this is a general tendency. You have very poor or in unstable complexes when you have tetra substituted systems, and they are not pictured here in this graph at all. So, here again, if you have this electron accepting property is quantified using the Hammett parameter, which you encounter in organic chemistry. The Hammett parameter is plotted on the x axis, then you will notice that as the Hammett constant becomes larger and larger, electron accepting property increases, and then the binding constant is increasing. So, there is a positive correlation between the two of them. So, the barrier to rotation is proportional to the extent of pi interaction. In general, you have better barriers to rotation when you have zero oxidation state metal complexes. The rhodium complex that we are going to talk about has got a barrier of 15 kilocalories per mole, but this barrier to rotation need not correlate with the frequency decrease. Frequency decrease independently correlates with the back bonding, but because there is a combination of steric effect and pi effect, these two need not correlate one with the other. So, here I have pictured for you what happens to the carbon-carbon bond distance when you have an electron withdrawing substituent. Here I have tetra 4 fluorines attached to the carbon, the olefins, and here I have simple ethylene. This distance is hardly increased from 1.34 angstroms. It has gone only to 1.36 angstroms. So, this is hardly a 0.2 angstrom increase in the case of the ethylene complex, whereas the carbon-carbon bond distance in the case of tetrafluoroethylene is almost similar to what you have for a carbon-carbon bond distance in diamond. So, carbon-carbon bond distance in diamond would be close to 1.54 angstroms, and that is pretty much what you have in the case of the tetrafluoro. So, there is a lot of electron density going in from the nickel to the pi star orbital, and this results in a very strong weakening population of the pi star and weakening of the carbon-carbon bond. So, there are some similarities between carbon monoxide and ethylene complexes. It is not just the case where you have eta 1 and eta 2 coordination modes between the ligand and the metal, eta 1 in the case of carbon monoxide and eta 2 in the case of ethylene. That is not the only difference, or that is not the only similarity. In terms of electron density donation from the HOMO, probably ethylene is a little better than carbon monoxide. HOMO in ethylene is bonding. So, when you remove electron density from the HOMO, it weakens the carbon-carbon bond. So, both carbon monoxide and ethylene accept electron density into the pi star orbital. So, this weakens the ethylene carbon-carbon double bond. And so, the CO on the other hand, it has got a slight difference because the HOMO is non-bonding if not slightly anti-bonding, And as I explained when we are discussing the carbon monoxide complexes, this is a controversial discussion that has been there in the literature, but it is understood that the carbon monoxide is not a bonding orbital. The highest occupied molecular orbital is not a bonding orbital, and so removal of electron density does not affect carbon monoxide significantly in terms of the CO stretch. So, a complete discussion of the metal olefin bonding and what we call as the Dewar-Duncanson model is given in a recent paper, which is pictured, which is the reference is given here. And what we have understood from all these aspects is a fact that olefin complexes can be readily synthesized, structurally characterized, and the bonding differences between carbon monoxide and olefins allow one to synthesize them by displacing carbon monoxide, and it is possible to have the significant reduction in the stretching frequency of olefin complexes due to the pi accepting nature of the olefins. And you can also use these metal olefin complexes to generate more stable olefin complexes by displacing them based on their pi accepting nature.